So finding the rates, finding the rates law using 4 methods. The first method would be the half-life method. Now let's say if r equals k e to the n, right? Let's say if n is 1, we know from previous examples that I showed that this is 0.693 over Ka, which is independent of concentration, of the initial concentration O. Then what I could do is this. You know that if n does not equal 1, it could be to the nth order. You could see that the half-life, you could see this from the previous videos, becomes A O n minus 1 n minus 1 Ka. Now the point of me doing this is I'm going to log both sides. I'm going to log 10 T half equals the log 10 2n minus 1 over A O n minus 1 n minus 1 Ka. Now by doing this, I'm going to, my goal is to have this by itself. So I could say log 10 2n minus 1 over n minus 1 Ka minus the log 10 A O n minus 1 equals the log 10 T half-life. Now bring it down. The log 10 T half-life equals the log 10 2n minus 1 over n minus 1 Ka minus the log 10, you know what, minus n minus 1, the log 10 concentration A O. Now this resembles something you learn in algebra. Y equals mx plus b. So if I were to make a graph of log in the y-axis of log 10 T half faces the graph of log 10 AO, the slope of the graph would be 1 minus n. That's the use of the half-life method, because by graphing this, you will get the slope. If you know the slope, you can find the value of the n. That's the first method. The next method is called, second method is called the powell method. Let me see if I spelled this name correct. Powell method. I'm not sure. Powell method. Yes. Now, if r equals K A to the n, right? Let's define dimensionless parameters. Let's call lambda equals A over AO, and that's defined tau, TAU, that's what it's called, as Ka concentration O n minus 1 T. Now let's go back to, this is called, lambda is called fraction of unreacted of concentration of A. Now back to this equation. The equation that I had earlier in the first video, ln AT of KAO minus KT. Now I could plug in, if I plug this into here, I would have ln lambda equals, if you see for n equals 1, this becomes 0, and then it will remain Ka times T, so this becomes minus tau for n equals 1. Now, you go back to the nth order reaction. N minus 1 Ka T. I'm going to plug this as lambda. If I minus 1 on both sides, and then I call this Ka An minus 1 T, and I call this tau n minus 1. So we have that An minus 1 T Ka should give you tau n minus 1 plus 1. So what I could do is this. If I were to log both, if I was to log both sides, I would have a log 10 lambda 1 minus n minus 1 equals log 10 tau n minus 1. So basically, T tau. So this, I could separate this more, and I can make it into tau plus log 10 n minus 1. Now, then I could say the log 10 of tau equals log 10 lambda 1 minus n minus 1 minus the log 10 n minus 1. So a graph of tau faces lambda. If a graph of tau faces log of lambda, would give you the Powell curves. And that's the point of that method. The next method is called the initial rates method. Initial rates method. Now let's say R equals K A alpha beta dot 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 2 L lambda. Now let's say we have a, let's take this back to Gen Chem. B dot 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 L, and the rates, initial values. Let's set up tables. Experiments. Let's have 2 experiments. Experiment 1, experiments 2. Let's have a concentration of this. Let's call this X1. Let's call this X2. Concentrations. This is in molarity, and this is in molarity. Now, this values, we don't know, but we have them fixed. We have in the rates. Let's call it RO1 and RO2. Now, the ratio of experiment 2 over experiment 1 will give you RO2 RO1 equals X2 over X1 alpha. From here, we could find what alpha is. depending on if depending on what x1 and x2 is. That's the initial rate method. The last method is called isolation method. Now I think I'm running out of papers. Let me get some papers. This is the initial method. Look at the initial method while I get blank new papers. Now, let's say the last method is the isolation method. Now let's say we have R equals K, A alpha, B, beta, dot dot dot, lambda. Now, the point of this method is to make the concentration of A, the initial concentration of A, so small, like much less than the concentration of B, and the concentration of every reactant. So we don't need this. If this is small, then this could remain constant. And then the rate will become K A lambda B beta 0 dot 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 L lambda O, which essentially would become K, let's call it J A alpha. So J equals K B O B dot 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 lambda O. So we could find alpha from the first method, from the half-life method or from the Powell method, and after we find alpha, we'll find J. This is the isolation method.